Good afternoon, Doctor. We are Group 19 from Session 11. Our group members are include me, Qin Chuanjun, Chu Haoxiong, and Doran Chiang Kai-hin. Today, I want to explain the GET design and the waveform for Project 2. So this is a 4-to-1 multiplexer with input I0 to I3 and select line S1 and S0. The select line and their complement generated by emitter, control 4, and gate is corresponding to one input. The AND gate output are combined through an OR gate to produce the final output Y based on the value of S1 and S0. This is a 16-to-1 multiplexer circuit created using 4-to-1 multiplexer. Each 4-to-1 multiplexer have 4 inputs, I0 to I3, controlled by 2 selection lines, S0 and S1. The output of these multiplexers are connected to a final state that combines them into one output, Y. This circuit is a 1-bit full adder. Inputs A, B, and C represent the 2 bits to add and the carry in. The sum S is calculated using 2 XOR gate, while the carry out Cout is determined by 3 AND gate and an OR gate. The design ensures correct addition and carry logic for a single bit. This circuit is a 4-bit binary adder using full adder. The inputs A and B represent 2 4-bit binary numbers to be added. Each full adder computes a sum and carries the overflow to the next stage. The least significant bit is processed by the first adder, while subsequent adder process higher bit using the carry from the previous state. The output labeled as represents the sum, and the final carryout is labeled as Cout. This is a 4-bit shift register made using D flip-flop. Each flip-flop receives input from the one before it. With the third flip-flop connect to the external input D-in, with every clock pulse, the data shift from one flip-flop to the next, turning serial data into parallel data. The output shows the current state of each flip-flop. This type of circuit is commonly used for temporary data storage, bit shifting, and serial communication in digital systems. This circuit combines data selection, arithmetic operation, and storage. It starts with two 4-to-1 multiplexer, each taking 4 4-bit input I0 to I3. The select line S controls which input is passed to the output YA and YB. The multiplexer output are fed into the ALU, which process the input. The ALU performs arithmetic or logic operation based on the C-in control signal. Its output are the result S and the carryout signal Cout, which indicate overflow in arithmetic operation. The result from the ALU is stored in a 4-bit register. The register is triggered by the clock signal to store data at each cycle, while the reset signal resets the stored data when needed. The register outputs the final value as Qout. This waveform demonstrates the functionality of our ALU design. Input A0 to A3 and B0 to B3 are the 4-bit binary value for A and B. This value changes at different points in the timeline, allowing us to test multiple cases. But in this waveform, we only use one input to check the ALU design. The A cell and B cell signal are 2-bit selected. This determines which inputs are active at any given time, controlling which data is processed by the ALU. The ALU OP signal selects the operation. When ALU OP equal to 1, the ALU performs addition, and when ALU OP equal to 0, it performs subtraction. For example, at 160 NF, with ALU OP equal to 1, the output ALU of out showing 0011, the sum of the A and B. At 400 NF, when ALU OP equal to 0, the output switches to subtraction, showing 1111. The clock signal draws the timing of the circuit and reset initially. ALU out changes dynamically based on this input, verifying the correct functionality of both addition and subtraction operations. This waveform confirms that the ALU operates as expected under different test cases. That's all from me. Thank you.